The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Welcome to a new lecturing of 8421. 8421 is an advanced course in atomic physics, graduate level course. 8421 is part of a 2-semester sequence in atomic physics. More naturally, 8421 is taken first in the sequence because we start with more basic things about light and atoms. But the course is designed in such a way that you can start with 8422 or 8421. So just to get an idea, who has already taken 8422? Should be about half the class. Okay, great. So yes, we are not repeating anything. And maybe for those of you, it's a little bit anticlimactic because you had all the fun. You saw all the great things which can be done with two-level systems. And now in this course we sit down and I explain to you what are those two levels. What happens to those two levels in magnetic field, in electric fields, how are they modified by the Lamb shift and all that. But you see how the two things are connected. I talk about some course formalities in a few moments, but let me first point out that you're interested or you're doing research in atomic physics at a really exciting time. AMO science is booming and is rapidly advancing. And a lot of it is really due to, well, of course, new insight, new ideas, new breakthrough, but also combined with technology. We have seen over the last couple of decades a major development in light sources. If I remember what lasers I have used in my PhD and what lasers you are using, wow, there's a big difference. Big difference in performance, but also big difference in reliability and convenience. But just a few systems which didn't exist a few decades ago are the Ti-Sapphire laser, which has really become the workhorse of generating lots and lots of power in the infrared domain, but then it can also be frequency doubled to the visible. When I was a postdoc in the early 90s, people just started to use diode lasers in atomic physics. Well, here you are 20 years later. We see much more solid-state lasers, and I would say even in the last 5 to 10 years, there has been another, well, revolution is too strong a word, but another major advance by having extremely high-power fiber lasers, which are covering more and more of the spectral range. So those advanced lasers in power and in spectral range, we have seen major advances in shaping short pulses. I remember when I was a student how femtosecond lasers were the latest. Well, they required a big laboratory, and femtosecond pulses could only be produced in a few laboratories in the world. With the discovery of the Ti-Sapphire laser and Kerr-Lenz mode locking, this has now become standard and is even commercially available. But researchers have pushed on, and attosecond pulses are now the frontier of the field. Well, if you have very short pulses, that also opens up the possibility to go to very high intensity. You don't need so much energy per pulse. You just, if the pulse is very short, you reach a very high intensity, which is in the range of terawatt. And it is now pretty standard if you focus the short pulse laser. In the focus of the short pulse laser, you create electric field strengths which are stronger than the electric field in an atom. So therefore, the dominant electric field is the one of the laser, and then you may add perturbatively or in whatever scheme the field between the electrons, or the electron and the proton. So this is the generation of light, but light also wants to be controlled, and this is done by using cavities. A single photon would just fly by, but if you want a photon to really intimately interact with an atom, maybe getting absorbed, emitted, emitted. If you really want to have the photon as a quantum state and not just as something which flies by, you need cavities, resonators. And we have really seen big advances in superconducting cavities, super coatings in the optical regime, and cavity QED in the optical and the microwave domain have led to major advances, and a series of spectacular experiments performed now with single photons. So the single photon is no longer an idealized concept for the description of light-atom interaction. It has been a reality, and single photon control has advanced quickly. Well, you can make major advances in terms of light, find new lasers, shorter pulses, higher intensity pulses, and things like this. But the other part of atomic physics, one is light, the other one are the atoms. We haven't invented new atoms yet. We still got stuck with the same periodic table, but we have modified the way how we can prepare and control atomic samples. A big revolution in the 90s or 80s has been the cooling of atoms, that now microkelvin, nanokelvin, and with evaporative cooling, even picokelvin regime has become possible. In terms of atomic samples, this was a revolution which took place during my time as a researcher. Atoms always meant you're the sample of individual atoms. Sometimes you studied interaction when two atoms were colliding, but atomic physics was really the physics of single particles or two particles interacting, colliding, or forming a molecule. But the moment we reach, through cooling, nanokelvin temperature, atoms move so slowly that they feel out each other. And that means suddenly we have a system to do many-body physics. So the advent of quantum degenerate gases and many developments after that with optical lattices and lots of bells and whistles really meant that, and this is dramatic, that atomic physics has made the transition from single and two particle physics to many-body physics. And for several research groups in the Center for Ultra-Cold Atoms, this is, of course, an important frontier. Well, somewhat related to that, but more generally, the precision in preparation manipulation which atomic physics has reached with quantum systems puts now atomic physics in a leading position at the forefront of exploring new aspects of Hilbert space. One can say that Hilbert space is vast, but what is realized with simple quantum system is only a tiny little corner of Hilbert space. And atomic physics, if I want to define it in the most abstract way, the goal is to master Hilbert space. And that means we want to harness parts of Hilbert space which are characterized by quantum entanglement, maybe in simple forms between two particles, but also between many particles. And of course, this has led to a whole new frontier in quantum computation and quantum information processing. So this sort of should show you that how technology, new ideas, control, manipulation is suddenly opening up whole new scientific directions. And just to add something more recent to the list, we have now a major research direction in AMO physics dealing with cold molecules, and there are even prospects of rewriting chapters of chemistry, what happens when you do chemistry, but not in the ordinary way, but at nano-Kelvin temperature, or what happens when you do chemistry, where you have coherent control in such a way that maybe the molecules before and after the reaction are in a coherent superposition state. So in that sense, the conclusion of that introduction is atomic physics has been successful because it continues to redefine itself. And to prove the case, I can say when I try to predict, I didn't even try because I know it wouldn't work, but if I try to predict 10 years ago what would be the hot topics of today, I would have failed. What happens is just breakthroughs and discoveries, and usually they happen in areas where they're not predicted. As another angle, atomic physics has seen more than its usual share of Nobel Prizes in the last 2 decades. Maybe the prize in 1989 for ion trapping in Ramsey spectroscopy. Ramsey spectroscopy is used for all generations of atomic clock. Ion trapping is the basic building block. This was sort of given for some of the technology, but this was the only prize in the long list I'm writing down now, which was given for something which was maybe invented a few decades ago. A lot of Nobel Prizes are given decades after the discovery. But all the more recent Nobel Prizes, and this speaks for the vitality of the field, were awarded for developments which had just happened in the decade before the prize. Whether it was laser cooling, just invented in the 80s, whether it was Bose-Einstein condensation, observed first 6 years before, the 2005 prize on precision spectroscopy with lasers and frequency comb. This was also a development, happened just a few years ago. And the most recent recognition for Serge Haroche and Dave Wineland is about the manipulation of individual quantum systems. And the highlights of this were accomplished just a few years, let's say over the last 5 or 10 years. Okay. Just sort of to make a general case here, I continue to be amazed how interesting and rich the physics of simple systems are. I actually expect that there may be even 2 Nobel Prizes in the near future for pretty much understanding the Schrödinger equation. You would say this has been done in the old days of quantum mechanics in the 20s and 30s, and of course lots of people have been recognized. But there are 2 aspects of the Schrödinger equation which hadn't been understood or which have been understood only recently. One is the aspect of entanglement and error correction. Nobody until 10 or 20 years, nobody until Shor and collaborators introduced error correction would have thought that a quantum system can decohere, but you can re-establish coherence by what is called quantum error correction. These are properties of the simple Schrödinger equation for just a few, well, qubits for a few particles, which were not known, or even the expert in the field would have flatly said, no, this is not possible. And another aspect of actually single particle quantum physics, which has been fully appreciated only recently, is the question of Berry phase and topological phase. All the rave in condensed matter physics, which is also spilling over to atomic physics, of quantum Hall effect, topological insulators and all that, means that there are non-trivial phases, non-trivial symmetries in the single particle Schrödinger equation. So just that as a case in point, that the single particle Schrödinger equation, a lot of people thought in the 40s and 50s, that's it, there's nothing else to do research. And now we see whole new fields emerging, exploiting new aspects of the Schrödinger equation. Will there be something else of the same caliber to be discovered? 20 years ago, people would have said no, and I just gave you two examples of major new insight which has really changed our understanding of quantum physics. A few years ago, I served on a National Academy of Science committee trying to do the impossible, to predict the future of the field. But sometimes the National Academy of Science is asked to give advice and try to provide the best wisdom possible, what is exciting. Of course, we didn't predict the future, but at least to the extent possible, we summarized what are the frontier areas where we see rapid development and where it would be worth investing further. And you will actually see that a number of those frontier areas are where your research happens. One is the traditional area of precision measurements. As long as atomic physics exists, one of the specialty of atomic physics is we can do precise measurements, atomic clocks and precision measurements of fundamental constants and all that. And that continues until the present day. It was just 2 weeks ago that there was a new Nature paper on the really major advance in atomic clocks. Strontium neutral atom clock has reached a precision of 6 × 10⁻18. It's amazing, we'll talk more about it. You really have to carefully understand and measure small changes in the black body radiation, because just the black body radiation creates frequency shifts which would interfere with that precision. An amazing accomplishment for the field. So precision measurements are continue to be an important frontier. Of course, there's always the aspect of metrology, determine time, frequency, and other things with higher and higher accuracy. But there are also applications. Just one example is magnetometry. Atomic physics methods can be now used. If you probe an atom in an environment, you can measure the magnetic field. So people are now talking by using atoms or artificial atoms in the form of MV centers to measure the magnetic field in biological cells and all that. So measurement has fundamental aspects, but has also applied aspects. Well, other frontiers are, of course, you can use the word ultra cold. We've talked about high intensity lasers, ultra intense, ultra short. Atomic physics is more and more getting involved with nanomaterials, materials with new properties, maybe materials with negative index of refraction, metamaterials, but in general, or plasmonic materials, nanomaterials, can help to shape light and explore new aspects of how light interacts with matter. And of course, a major frontier is the frontier of quantum information. So, given all this excitement, you have many reasons to want to learn more about it, and this course is definitely a good starting point. Let me maybe tell you a little bit what is the philosophy behind the course and what you will get. That means, of course, at the same time, what you will not get. This course is meant as a systematic, basic introduction into AMO physics. It should really lay the basic foundation that when you talk about atoms, when you talk about light, you are really an expert and you can talk about it at the most profound level. So it's important here, and this is the goal of this course, to provide enough knowledge, enough foundation for that. So it's not a course where I just try to sample highlights of the field and provide you with a semi-understanding of all these wonderful phenomena. I rather try to focus on selected basic things, but then also, exciting things, but rather explain them thoroughly and teach you by example than teaching you a big overview. The course, if I want to characterize it, I would say it is a conservative course. It's also, in this sense, traditional. One reason for that is MIT, the tradition we have at MIT. At MIT we have this several generation of atomic physicists who have shaped the field, and I learned atomic physics as a postdoc from Dave Pritchard, who was a graduate student of Dan Kleppner. Dan Kleppner was a graduate student from Norman Ramsey. And Norman Ramsey was a postdoc with I.I. Rabi. And Rabi resonances, RF resonances, this is the beginning of atomic physics. The resonances, that's what we will also focus on today and in the first week. This is sort of the most important concept in atomic physics, to really understand the nature of resonances and all its implications. So I should say, late in my life, I was already past 30 when I took the first atomic physics class in my life. I took it from Dave Pritchard, and I was really sort of amazed about a course which had the traditional topics but provided a lot of insight. You can teach traditional physics from the perspective of somebody who does research today. So I want to give you all connections, but at the same time, I like a lot about a traditional approach, and some of it can be traced back to Norman Ramsey. So eventually, over the last years, I was the main person who has shaped the atomic physics course. When I expanded it from 1 semester to 2 semesters, but when I created a lot of new topics, I always looked through Dan's and Dave's note and made sure the best of what they taught, the best ideas they put into the course, they still survive until the present day. So this course is a development and continuation of a long-standing tradition. I should say I have immensely enjoyed to co-teach the course on a couple of occasions with Vladan Vuletic and Ike Schwang. And Ike has made major contribution to the second part of the course, and Vladan especially to what we will be discussing in the next few weeks. So what I think is unusual, you won't find it in many textbooks, is that we start out by discussing the phenomenon of resonance of the harmonic oscillator, and we will emphasize for a while the classical part, but then also, of course, go to quantum mechanical aspects of resonance. And I have to say, this balance between classical and quantum mechanics is something I will emphasize again and again in the course. I can guarantee you in this course, I will sometimes ask you interesting questions which challenge your intuition. And you will most likely recognize that often when your intuition goes completely wrong, it happens because you believe too much or you overinterpret one aspect of quantum physics. If I then tell you, but wait a moment, now think classically, push the classical concept further, regard the electron in the atom as an harmonic oscillator, regard light scattering as the effect not of a quantum mechanical atom, but of a driven harmonic oscillator. Suddenly, a lot of things which come out of quantum mechanics make much more sense. So I've often seen when I had a conflict in my understanding and there is a semi-classical and a quantum mechanical explanation, I've learned to trust much more the semi-classical explanation. So that's why I feel it is important to understand the classical aspects. And usually I would also say understanding means to really understand its limits. And often I feel you can understand the phenomenon only when you have a quantum aspect, a classical aspect, and you know exactly where they overlap and where they differ. So to see even quantum mechanical objects occasionally from the classical perspective provides additional insight. So therefore, I will emphasize classical aspects. And for instance, it may come for many of you as a surprise, and you will see that next week, that some aspects like the generalized Rabi frequency, which you've all or many of you have seen for a two-level system, will find it in classical resonance, just the classical equation of motion of a gyroscope has a generalized Rabi frequency. And I do feel that it is absolutely important for the understanding of concepts, that you know where do the concepts emerge, where are they? Are they already there in classical physics and survive in quantum physics, or is it something new which is genuinely quantum? So yes, I will teach a little bit more classical physics than in a standard AMO course, but because I've seen within my own research experience that it helped me to shape the intuition for a fuller understanding of the systems we are dealing with. So resonance is an overarching theme here, but then we have to introduce our main players. The atoms come to stage, and we want to understand the electronic structure, the fine structure, the hyperfine structure. We want to understand what happens in magnetic, electric, and electromagnetic light fields. We want to understand in a deep way how do atoms interact with radiation. This also leads us, there is a big difference. You would say, well, what's the difference when atoms interact with microwave and atoms interact with light? Well, light, or at high frequency, spontaneous emission becomes important, and then you have an open quantum system. You have a Hamiltonian which couples automatically to many, many states. So that's why radiation is different from just electric and magnetic fields, because of the presence of all the vacuum modes, and we'll talk a lot about it. There's one special aspect about the course which I don't think I've seen in textbooks in the same way. We are singling out in a rather long unit the aspect of line shape. I mean, okay, we talk a lot about an atom has a resonance, but when we measure the resonance, there is a line shape. And I found it extremely insightful when I first saw Dave Pritchard doing it in his atomic physics course, to just talk about all aspects which modify a resonance from a delta function, from a stick diagram, into a real shape. It can be Doppler broadening, it can be finite lifetime broadening, it can be inhomogeneous field, but there are lots of interesting effects, and by discussing them all together, you gain major insight. So we discuss how photon recoil, how the velocity of the atoms affects the line shape, and if you think you've understood everything, I will talk to you about a very counterintuitive aspect of line shapes, namely Dicke narrowing. If you put atoms in environment, you would say, and they collide, this should lead to collisional broadening. But there is one aspect where collisions lead to narrowing, and that's sort of a highlight of this chapter, which really sort of shows you how all those broadening mechanisms are somehow connected. Finally, and this puts us towards the end of the course, we want to understand what happens when atoms interact not just with one photon but several photons, and then we talk about multi-photon processes. I should actually say that I'm also emphasizing the multi-photon process a lot. I mean, often we just think we do a transition between two levels, and there is an operator, it can be single photon or two photon operator. Yes, but to understand the multi-photon aspect is important, and maybe to just give you one aspect of it, when you think you do one photon physics, often you do two photon physics. A lot of people think atoms can absorb a photon. I've never seen in my life an atom which has absorbed a photon. The photon is immediately re-emitted. It's a scattering event. An atom cannot absorb a photon for good because the lifetime of the excited state is short. So when you think absorption is a single photon event, there is a limitation where, yes, you are allowed to think about it, but if you get confused, and I will confuse you, then you need the fact that every absorption process is actually a two-photon process, photon in, photon out. And sometimes by remembering that it's not single photon, there are always two photons involved, it helps you to avoid some pitfalls of the single photon picture. So therefore, multi-photon, yes, it's not just high-intensity two-photon transitions in atomic hydrogen or such, it's also about a deeper understanding how does a single photon interact with atoms. And finally, there is something which has fascinated many physicists, the question about coherence. And coherence is as fascinating as it is diverse, because coherence has many aspects and has many implications. And I also like a lot in this traditional MIT course that coherence is sort of singled out as a chapter, and now I tell you about all the different phases of coherence in this chapter and not scattered throughout the whole course. We have coherence in single atoms. The simplest one is a coherent superposition of two levels, which is so simple that it's almost boring. But there is an enormous richness when we put in a third level. About 20 years ago, an understanding of three-level physics has really created a new frontier in the field. Let me just tell you buzzwords: lasing without inversion, electromagnetically induced resonance. Those concepts happen due to coherence between three levels. And we'll talk about them towards the end of the course. Well, we have coherence within an atom between two different or three different energy levels, but we can have also coherence between atoms. And at that point, the atoms interact not individually, they act collectively. And of course, coherence between atoms can be the coherence of many atoms in a Bose-Einstein condensate, where they form one big matter wave. But it can also be the coherence. The atoms are not coherent because they form the Bose-Einstein condensate, but they interact in a coherent way with light. So there is only one aspect where the atoms act coherently. They may be in different quantum states, but the interaction with the light is absolutely identical. And when it then comes to optical properties of the system, the light doesn't care if the atoms are different. The light only cares whether the atoms interact with the light in an absolute identical way, and then you have certain symmetries of the light-atom interaction. And this coherence between many atoms in the interaction with light leads to, I just give you the buzzwords, is responsible for the process of phase matching. When you have a crystal and frequency double laser light, you want all the atoms to interact coherently. And it is also important for the phenomenon of superradiance. I found this subject of coherence particularly fascinating. I should say it was the subject of coherence where maybe 10 years ago, I was in a long-lasting controversy with some colleagues in my field. You know, there are people like Bill Phillips. When I meet him, he's one of the smartest, atomic physicists and one of the fastest one, and ideas just fly back and forth. And there was only one example where we disagreed over a long period of time, where he had good intuitive arguments, I had good intuitive arguments, and we couldn't agree. And this was related to the question when it came to atom amplification, some coherent process, whether it is really necessary to have a Bose-Einstein condensate, or whether you can get away with less, which is more the superradiant way, where the atoms are in different states, but they have an identical way to interact with light. And in the end, I could prove that certain aspects which all people thought in the field were due to the coherent nature of atoms, were due to the fact that these atoms can be regarded as an atom laser. It was just some form of superradiance in disguise. So anyway, you will notice some of my own interest in the chapter of coherence when I teach it. So it's something which is, yes, phase matching and superradiance is the physics of the 50s, but a deeper understanding of it really developed when we had Bose-Einstein condensates and could put some of those ideas to the test. So that's what you expect. That's an overview over the topics. The course will have 26 lectures, and these are the topics we cover. Do you have any questions about the syllabus and the structure of the course? There's something I want to say about homework. This semester, Ike Schwang has teamed up with me, and as many of you know, Ike is one of the real drivers of MIT edX and digital learning at MIT. So he is now teaming up with me and trying to put some of the P-sets online, that you can have conceptual questions where you can work on, and you will get immediately feedback whether you are on the right track or not. So this is a new element which we want to introduce to the course. I still think there are certain problems you have to just sit down with a white piece of paper, not knowing what to write, and start scribbling some equations. So we'll have conventional problems, but we also want to experiment to what degree is it possible to use elements of new technology of digital learning for a course like that. Actually, I have to say, I regard it as a really very interesting and promising experiment to have some aspects of digital learning in a graduate course. When MIT does MITx and broadcasting education to the whole world, it's much easier to think about what to do when you have a basic introduction into classical physics, into circuit design. There is sort of a standard curriculum. A lot of questions are simple. It's pretty pretty straightforward how you can have simple questions as multiple choice questions. But this is different. This is really a graduate course in atomic physics is about deep and profound understanding of complicated and complex physics. I'm not sure to what extent those complexity can be broken into smaller elements which can be put up as multiple choice questions. Probably not. But on the other hand, since MIT will never reach millions of people with a graduate course in atomic physics, the whole interest of going to the whole world and reaching the whole world is absent. And for me, I just want to introduce this technology to increase the residential experience for you students. So for instance, videotaping, I'm not sure if these videotapes will ever be shown to a worldwide audience. We probably make them available, but the primary audience may be people like you who have a conflict in attending a class and you want to check what was presented in class. I also have the idea, but this would be in the future, once we have the videotapes, maybe I can tell you, look at the video recording of the class, and instead of having a lecture, we just have a classroom discussion. So these are aspects I want to experiment, but it's sort of exciting to see how can new technology be used for a course which is very, very different from all the other courses which have been put online at MIT. Well, then, as expected, we have some 20 minutes to start with our first topic. Which is resonance. And resonance is what describes what is relevant for two-level systems, and also, and we will touch upon this, resonances are the way how precision measurements are made. So, what is a resonance? Well, we can first look at a classical resonance. Well, a resonance is something where we have some variable and it varies periodically. So, in other words, yes, there is a variable which can be anything. It can be the population, a quantum state, it can be an electric field, it can be the position of an atom, it can be anything you can think about it, anything you can measure. And if this variable varies periodically, you have a resonance. Of course, the periodic variation usually requires that you drive the system. So you first drive it, and then the system oscillates. And this means now that when you drive the system, so this may be a free oscillation, but now you drive the system with a variable frequency, and what you then observe is you observe a peak. So the phenomenon of resonance is that you have something which can periodically vary, and when you drive it, you see peaked response when driven with a variable frequency. Yep, this is pretty basic, and I don't want to dwell much more about it, but I can tell you we are interested in atomic physics in every single possible aspect of this resonance. The shape of the curve, how we can modify it, what happens when we drive it strongly, when we drive it weakly. I mean, this resonance is really the language we talk to atoms with. So, but here I just want to give a light-hearted introduction. The first thing we want to add to the phenomenon that there is a resonance at a certain frequency is finite damping. That would mean that after the system is driven, the oscillation does not last for an infinite amount of time. And that implies that when we drive the system and look at the response as a function of frequency, there is a finite width delta f for the driven system. And as we will see in many ways, the damping time and delta f are related by a Fourier transform. And we usually characterize oscillators by the sharpness of the resonance. And the sharpness of the resonance is the ratio of the width of the resonance and the frequency or the inverse of it. So if you have an oscillator at a kilohertz and the resonance is 1 hertz wide, we say the resonance has a Q, a quality factor of 1,000, and that means you can observe 1,000 oscillations before the oscillation decays away. So what is special about atomic physics here? Why do I emphasize that in the introduction of an atomic physics course? Well, the system is that in atomic physics we often have exquisitely isolated systems, an atom in an ultra-high vacuum chamber, or systems which are prepared with all the tools and the precision which we have developed over decades in atomic physics. And therefore the result is that in atomic physics our oscillators are characterized by an extremely high quality factor Q. And let me give you an example. If we look at an optical excitation, maybe let me point out that something you all should try when you take a class in atomic physics, or even more so when you do research in atomic physics, that you have a few numbers in your mind which match. So, you know, every single person in this room should know what is the frequency of light. How many hertz is? What is the frequency of a laser? The number I usually use for those estimates is 10 to the 15 hertz. Who knows what wavelength this laser is? 10 to the 15 hertz is? Well, I've used some visible light, but the speed of light is 3 times 10 to the 10. So therefore, if I just use the power 10 to the 15 hertz, it has to be 300 nanometers. Okay, so never forget that for the rest of your life. 300 nanometer is 10 to the 15 hertz. That means the most of us who are working with rubidium, lithium, and sodium, which is 600 nanometer or 800 nanometer, the frequency is more 5 times 10 to the 14 or 3 times 10 to the 14. But just as a ballpark number, 10 to the 15 hertz is 300 nanometer. Okay, so if we have an optical excitation, and many atoms have that, what is the Q? What is the quality factor of this resonance? Well, when you stabilize your laser to a vapor cell and you look at the resonance, then you observe in a vapor cell that you have room temperature Doppler broadening. We talk about Doppler broadening later in this course. That usually corresponds to a frequency width on the order of a gigahertz. And that means that your quality factor is on the order of 2 times 10, is on the order of 10 to the 6. A million, that's pretty good, a million oscillation. It's a very pure oscillator. But of course you can do much better if you do Doppler-free spectroscopy, either by having an atomic beam which is intersected at right angle, or even better, put the atoms in an optical lattice. And this is what people are now doing with the optical lattice clocks, that they put an atom in an optical lattice where the Doppler broadening is completely eliminated. If you take a metastable level, that the lifetime of the excited state is maybe 1 second, and strontium and other atoms have those metastable levels, then you can actually get a line width which is 1 Hertz, and the Q factor is on the order of 10 to the 15. I will show you a graph and an example of such an experiment, and 1 Hertz line width of an optical transition for an optical atomic clock experiment in the next class on Monday, when I want to discuss other aspects of it. But this is one of the world's best oscillator you can imagine. 10 to the 15. It's a mind-boggling number. Well, it's clear why clocks have gone atomic. Mechanical systems are actually not bad, but of course not nearly as good. If you take quartz oscillator, well, you can build pretty good clocks out of quartz oscillators. You have quality factors which vary between a few thousands and a million. The best values are reached at low temperature. And actually, even in the advent of atomic clocks, quartz oscillators or sapphire oscillators still play a role, because you need sort of flywheels. An atomic clock you may interrogate only every Ramsey spectroscopy, every tenth of seconds. You get a signal, and in between you need a flywheel. And then clocks, which have a very high signal-to-noise ratio but not the accuracy, help you to interpolate between measurements. We see actually a renaissance of mechanical systems in the form of micromechanical oscillators. It was only achieved in the last 2 or 3 years that micromechanical oscillators could be cooled to the absolute ground state. And there is a lot of interest of coupling the motion of a mechanical oscillator to an atomic oscillator, because they have different properties, and for quantum computation and other explorations of Hilbert space, you want to have different oscillators and combine the best of their properties. So therefore there is a real renaissance in mechanical oscillators, and those micromechanical oscillators have often quality factors of 10 to the 5. Here is, I want to show you a picture of a fairly nice one. this is a micro-fabricated device. It looks like a little mushroom. And what happens is this mushroom-type structure can confine light which travels around the perimeter as a so-called whispering gallery mode. It's similar to an acoustic mode which can travel in the dome of a big cathedral. That's how it was discovered. It's an amazing effect. I wish somebody would demonstrate it to me, but if you go to one of the ancient cathedrals and you're in a dome, somebody can talk in one direction, the sound can travel around and you can hear it. There's a guided special mode which can travel around the perimeter of a dome, and here in the microscopic domain, it's light which is confined in such a resonator. So this is a resonator for whispering gallery mode, and that can have a Q on the order of 1 billion. So the idea here is that you have either one of those mushrooms or a glass sphere, and the light can sort of travel around. And this is the characteristics of this mode. Well, you can go from a tiny glass sphere to astronomical dimensions. And you also find oscillators, and the Q of those oscillators is not really bad. How good is the Q of the rotation of the Earth? It fulfills all of our requirements for resonance and oscillator. It's a periodic phenomenon. The Earth goes, the Earth rotates around the sun once a year, and the question is, how stable is it? Well, the number is 10 to the 7. It has a Q of 10 to the 7. So the precision of the rotation of the Earth is better than 1 part in a million. You can also look at the rotation of neutron star. If those neutron stars emit flashes of X-rays, these are pulsars, and you can measure the rotation of neutron stars. Those neutron stars have a quality factor of 10 to the 10. And of course, if, as the name says, if a resonance has a high quality factor, it can be used for quality research. The narrower the line is, the more sensitive you are to tiny little changes. And you probably know this pulsar with a Q of 10 to the 10, well, has been used for the first, also indirect, observation of gravitational waves. The pulsar rotates with a very precise frequency, and you can measure it with 1 part of 10 to the 10. And people have seen that over the years, the frequency of rotation became smaller. And you can figure out that it becomes smaller by just 1 part in 10 to the 10, because you have this precision. And what happens is, when a pulsar rotates, when a neutron star rotates, it emits gravitational waves, and the gravitational wave is energy which is taken away from the kinetic energy of the rotation, and therefore the pulsar slows down. So having an oscillator with such a high Q has allowed researchers to find a small effect in the damping of this oscillator, which in this case were gravitational waves. Of course, the story I will tell you is about very small changes of atomic oscillators which led to the discovery of the lamp shift and to quantum electrodynamics. But the story is the same. A high-quality oscillator is the tool for discovery. Okay, so we've talked about resonances. Of course, there are resonances which are useful and others which are less useful. By useful, we mean they're reproducible. You can really make a measurement and trust it and repeat it and do it again. And that's not enough for being useful. You also want to learn something about it. So we usually regard resonances as useful when they are connected to, by theory, to something we are interested in. It can either be fundamental constants or, well, let me say, other parameters of interest. If you want to measure a magnetic field with very high precision and you look at atomic resonance, it's only useful when you have a theory which tells you how the shift or the broadening of the resonance is related to magnetic fields. And this is again a specialty of AMO physics. We have plenty of resonances which are useful by those standards. And if we compare to astrophysical oscillators or quartz oscillators or fabricated oscillators, in atomic physics, we have the great advantage that atoms are identical. We know when we measure a transition in atomic hydrogen in Japan, in Europe, and in the United States, the value has to be the same. For other oscillators, you often don't know that. And the sort of showcase of atomic physics is the Rydberg constant, which is the best known, the most accurately known constant in all of physics. And the reason is because it can be directly measured by performing spectroscopy in hydrogen with highly stabilized lasers. Okay, of course, the question is, who's interested in all those digits? Why do you want to spend all of your PhD or half of your life in measuring the Rydberg constant to maybe 10 times more precision? Well, it depends. It's maybe not something for everybody, but there are some connoisseurs who think that every digit has provided new insight into nature. And let me just give you one example. If you measure the Rydberg constant very precisely, you can now, and this has become a frontier of our field, ask the question, is there a change with time of fundamental constants? So when you measure the Rydberg constant today with 10 to the minus 15 precision and measure it again in a year, who is guaranteeing to you that you will measure the same value? So with the precision which I've just given to you in this measurement of the Rydberg constant, people are now able to say whether the Rydberg constant has changed 10 to the minus 15 per year. Of course, you know the age of the universe is 14 billion years. That's about 10 to the 10 years. So even the worst case is that if you would go back to the beginning of the universe and the Rydberg constant would change at 10 to the minus 15 per year, it would have changed by 10 to the minus 5 over the age of the universe. But this would be dramatic, because you can actually show that life would not have developed, the whole organic chemistry would have been different if some fundamental constants of nature had been different by 1 part in 10 to the minus 6, 7, or 8. So you have extremely stringent limits how much fundamental constant could have changed during the evolution of life, because life would not have been the same if fundamental constant had changed. The question, of course, is, should those fundamental constants change? Well, the answer is we don't know, but there is a whole research area in string theory where they say that our universe is sort of just one of many possible minima in a multidimensional space, and it's actually a dynamic minimum, and it may change as a function of time. So there are people who wouldn't be surprised if the world is not the same in the future as it is right now, because the universe, or whatever defines fundamental constants, is changing as a function of time. So the question is, will it be during your lifetime, or will it even be during maybe your PhD, that one researcher says, we now have an error bar and we find out that yes, we measure fundamental constant using the most accurate atomic clock, and a year later we have measured something which is a tiny bit but significantly different. The second aspect why you should always measure things as accurately as possible, and this is sort of the tradition in our field. If you can measure something very accurately, do it, because yes, there may be surprises. And for instance, when people looked at the Zeeman shift with higher precision, they found, we will talk about it when we talk about atoms in the magnetic field, when people looked at the anomalous Zeeman effect, the discovery of that is what nobody expected, that particles electron has a spin. Or when people saw a tiny shift in the spectrum of atomic hydrogen, it was 1,000 megahertz splitting. It was the lamp shift. This was the discovery of quantum electrodynamics. And we know that precision always becomes a tool to control atomic systems, control quantum mechanics with more precision. For instance, if you can completely resolve hyperfine structure, you can prepare atoms in a certain hyperfine state. If you don't have the resolution, you can't do that. Okay, so we now want to go back to the resonance. When we look at typical resonance, we have a frequency omega, a resonance frequency omega naught, and we measure line widths delta omega. In many cases, and we will discuss them in great detail, the line shape is a Lorentzian. And the Lorentzian is the imaginary part of a 1 over x function, omega naught minus omega. And then there is this parameter gamma. Gamma, which appears in the Lorentzian, is identical to the full width at half maximum, and the Q factor of a Lorentzian is omega naught over gamma. Let me finish 3 more minutes with a short note about a I've talked about resonances, I've talked about now the two important parameters, the resonance frequency and the full width at half maximum. How do we measure those? And there is actually sometimes a confusion. The most systematic approach is you should measure all those frequency and line widths in angular frequency units. Which are technically radian per second, 2 pi per second. But since radian has no dimension, we sometimes say we measure it in inverse seconds. So this is the measurement of angular frequencies, and this is different from the unit of frequencies. When we have a frequency, which is an angular frequency divided by 2 pi, frequencies are usually measured in hertz. The problem is that a hertz is always also 1 over a second, and this is where the confusion comes. So let me just point out that how you can avoid the confusion. You may write an angular frequency omega naught. It is 2 pi times 1 megahertz. Then you exactly know what it is. You can, of course, this is nothing else than 6 times 6.28 times 10 to the 6 second to the minus 1. But you should never say that omega naught is 6.8 times 10 to the 6 hertz. Because then people don't really know, and you get confused, and you confuse other people, if you really mean that this is now, has a frequency of 6 times 10 to the 6 hertz or an angular frequency. So just be clean in your thinking, in your homework and all that, that a frequency, when you mean angular frequency, is 1 over second. When you mean it as a frequency, it's hertz. And this is often the clearest form to say, yes, I know where to put the 2 pi, and I put it in explicitly. So we often in our papers report frequencies like that. Finally, there is the question about gamma. So what are the units for gamma? Well, if you look at the exponential which decays, it has e to the minus I omega t, and then it has the imaginary part, gamma t. So gamma is really a temporal decay, and there is no question about frequency and angular frequency. It's not a frequency, it's not an angular frequency, it's a decay rate. So for instance, if gamma is 10 to the 4 per second, you should never say gamma is 10 to the 4 hertz, or you should also never say gamma is 2 pi times 1.66 kilohertz. That just doesn't make any sense. Gamma is really a damping rate.
Okay.
Yes? I need 1 more minute.
Okay.
And is therefore an inverse time. The damping time associated with this gamma is simply the inverse of it, and in the case chosen, it's 100 microseconds. So just keep that in mind. Time is over. Any question? Okay, great. We meet again, same place, same time on Monday.